Good day, ladies and gentlemen. We are going to begin our discussion of exponentials and logarithms. The two are really one and the same, and that's why we study them together. I'm going to operate under the assumption at this point that you all have the exponent rules handled, and you're okay with them. We're going to proceed with the rest of this stuff. If you don't really remember the exponent laws, you're going to need to go back and find a way to review those because, well, they're something you just need to know at this point. So we're going to start out looking at exponential functions. And an exponential function is something of the type f of x equals b to the x. b is a real number, and x is the variable. That's our independent variable, and it's in the exponent of this function. That's how we know it's an exponential type function. So for these functions, the domain is always all real numbers. X can be any real number we want. The range, however, the range is the set of y's such that y is greater than 0. It can never be 0. It can only get really, really, really close to 0. The y-intercept, if I plug x equals 0 in, anything to the 0 power, any real number to the 0 is going to be 1. So the y-intercept is 0, 1, and the x-intercept, there is none. What we have is a horizontal asymptote which is y equals 0. This graph approaches y equals 0, but never gets there. For the graphs, notice I have two coordinate planes here because the graphs can look one of two ways. If b is greater than 1, we get a graph looking like that with our horizontal asymptote, y equals 0, our y-intercept of 0, 1, and we have growth. If the base is greater than 1, we have an exponential growth curve. If b is less than 1, but also greater than 0, we don't want b to be 0. That wouldn't be an interesting graph to us. And if b is negative, it's just weird. We don't get a nice curve if b is negative. So if b is between 0 and 1, so if it's a fractional value, we're going to get a curve that looks like this. Again, y-intercept of 0, 1, and asymptote y equals 0, but this time it's exponential decay. It's a decay curve if b is a fractional value between 0 and 1. So let's look at an example. Oh boy, look at this one. This one looks awesome fun, right? We've got a coefficient of -2. We've got the x minus 1, the exponent of plus 3 outside. Wow, how are we going to do this? So I'm going to start with just y equals 3 to the x. So for this one, 0, 1, and 1, 3, and my curve would be going like that. But that's not the curve that I want to graph. We need to stretch it by a factor of 2 and reflect it across the y-axis. Okay, so this point gets stretched by a factor of 2 and then reflected across, so it is now at -2. And then this point, 1, 3, not 1, 4, should be there. That's going to get stretched up to 6 and then reflected across. So this graph has gotten steeper. Now, the asymptote would still be right there, And if I didn't have the translations, my curve would go like that. But we have translations. So I need to now take these points and translate them using the vector 1, 3, which means go right 1, up 3. So right 1, up 3. 1, 2, 3. Right 1, up 3. Erase some of these other points that I don't need anymore. And remember, the asymptote must shift also. And there's our graph. Now, if we wanted to find a more precise place that it crosses the y-axis, we would, of course, have to plug in 0 there to find that would be our x-intercept. If we plug 0 in for x, we would get the y-intercept. And let's go ahead and find that. So y equals negative 2 times 3 to the negative first it would be, plus 3. So this is negative 2 times 1/3 plus 3. So negative 2/3 plus 3 is 2 1/3. So we could better represent that point on our graph. To find the x-intercept, it's going to be a bit more involved. And at this point, we would need to use our graphing calculator to do this, or if we have knowledge of logarithms, we could go that way. But let's keep moving. We're going to look at exponential growth and decay models for situations. A sub 0 is our initial amount. B is our growth factor or our decay factor. Remember, if we're growing, B has to be greater than 1. If we're decaying, B needs to be less than 1. And T is number of time periods. Let's do an example related to half-life. So we know the half-life of carbon-14 is 5,730 years. How much would remain after 15,000 years? Whoa. Okay, so we need to know what R is. So if we're starting with 10, we know the half-life is this. So half is left, that means the amount is 5, R to the 5730. That's the decay model that I just showed you. Amount is equal to initial amount times the rate raised to the number of years. So 1/2 equals R to the 5730. R is going to be the 5,730th root of 1/2, also known as 1/2 to the 1 over 5730. So my model becomes A equals 10 times 1/2 to the 1 over 5730. Remember, that's just a root to the t. So we're going to drop 15,000 in to the t. Using our laws of exponents, this becomes 1/2 to the 15,000 over 5730. And what we find is this is approximately, to 3 significant digits, 1.63 grams. But the first step in doing something like this is figuring out what that ratio or what that rate of decay is. How much per year are we decaying? Compound interest, another exponential growth decay kind of model. This formula looks a little bit different, but this thing right here is our growth factor. Now, why 1 plus R? Well, 1 plus R allows us to take 100% and add on, say, 4% interest, giving us 104% of what we had. Why do we have R divided by N, though? Well, sometimes certain accounts don't just pay you interest every year. They might pay you every month, or they might pay you every day, or they might pay you every quarter. And for those situations, you don't get that percentage every single time. What they do is they chop that percentage up into that many pieces. And then that takes the number of time periods and increases it also. So if it's 4 years and it's monthly, that's going to be 48 times that we're getting this interest payment. That's why we're doing N times T up here. So let's put this into context and see if we can't fit things into this formula. So, 1,000 euros, 5.25%. Find amounts in the account after 8 years if interest is compounded 1, 2, 3, 4, 5 different ways. All right, so let's start with annually. The amount will be 1,000, 1 plus 0.0525. Percents must be used as a decimal, and N here is 1. It's 1 time per year. So I just raise this to the 8th, and I get 1,505.83. Semi-annually. That means 2 times per year, so N is equal to 2. We start the same, 1 plus 0.0525, but we have to chop that in half because we get half of that interest the first half of the year, the rest of the interest the second half of the year, and in the exponent we're going to do 8 times 2. And we find that we get a little bit more money this way, 1,513.74. Quarterly. That means N is 4 times a year. A equals 1,000. 1 plus 0.0525 over 4 raised up to the 8 times 4. 4 times each year. That's a total of 32 times that we're getting paid interest. And what do you know? We make a little bit more money. 1,517.81. So why don't you guys pause the video and find the monthly and daily total and see what you get, and then restart the video and see if we get the same thing. So monthly, you should recognize that N is 12. And we're making 1,520.57. And finally, daily, N is equal to 365. We're assuming it is not a leap year. And we make 1,521.92. And there is another way that we could get interest, and that's interest paid continuously, and we will look at that in the next video.